Welcome to the video demonstration of the Boulder Detection 2D Radix Pro interactive tool, which is located here in the interactive tools section of Radix Pro. Note that Boulder Detection is licensed separately from the Radix Pro processing package. Here I will talk about the data preparation for Boulder Detection and the Boulder Detection itself using this small demo project. The project is available upon request together with the Boulder Detection 2D trial license. The first step in the project is data input. Here I loaded the data into the project interactively, so we can just inspect it. The data I use here is a single channel survey, although one can detect boulders on a seismic stack in a similar way. If we plot this, we can see relatively flat layering with a few boulders in the near surface, which cause these diffractions here. Note that while we are focusing on only one line, the interactive boulder detection tool can handle several lines at a time. The next attribute computation flow handles data preparation for boulder detection. The 2D boulder detection module needs the original seismic data as well as a boulder detection attribute. Ideally, the boulder detection attribute needs to be a dataset which contains the probability of a boulder existing at each sample in the seismic line. Still, providing any dataset which has higher amplitudes at boulder locations can be good enough. We will compute such dataset using diffraction imaging. This flow first separates the diffractions from the original data with the structural smoothing module. Structural smoothing computes the dip of the reflections in the specified windows, then smooths the data along these dips, obtaining the reflections, and in this case subtracts the reflections from the data to finally obtain the diffractions. Let's inspect the diffractions. Here you can see that the reflections have been successfully removed and the diffractions caused by boulders are shown here. The next part of the workflow is the power of trace module, which just conducts some heuristic amplitude scaling. It computes the so-called nth root wave field, which is explained in detail in our diffraction imaging tutorial on the website. It here just amplifies the diffraction tails relative to the apexes, and this emphasis on the diffraction tails just allows us to emphasize the diffractions in the following migration result. Let's run this flow. Next, we migrate the diffractions. The diffractions are input here. We migrate them just like we would normally migrate our conventional data, or 2D post-stack migration with an aperture we set. The only difference here is that the shaping filter is turned off. Let's run the migration and inspect the migration result. As expected, the migration focuses the diffraction energy around the diffraction apex where the boulder is located. Finally, we take this migration result and compute an attribute called diffraction energy. Basically, we just square the migration result with the power of trace module. We also add the line number header here, and we'll conduct 2D special filtering just to get a smoother attribute. And this is how the attribute looks like. And if we compare this attribute to our diffractions, we will see that the attribute has high amplitudes at the diffraction apexes, basically at the boulder locations. Now we just need to save our diffraction attribute to the dataset located near the original data in the same directory with a specific suffix in the name which we will specify in the boulder detection parameters. Finally, we go to the last flow, which conducts boulder detection. It only has the interactive boulder detection 2D standalone module. In the parameters of the boulder detection, one specifies the seismic lines. Here we have only one seismic line, the time interval for the analysis, which is 5 to 25 milliseconds here. As mentioned previously, the suffix for the boulder detection attribute specifies what is the name of the boulder detection attribute dataset relative to the current line name. Then we set the nominal CDP spacing of the survey, which needs to be the same for all the studied lines. And these parameters in green, the thresholds, the filters will be set interactively, so we keep the default values here. And finally, the module scheme at the bottom keeps the interactive progress so that the user can resume the work at a later time after closing the module. When launching the boulder detection module, we get a plot of one of the seismic lines. If there are several lines, one can scroll through them here at the top. First, we compare the attribute to the data. Indeed, we see that the amplitude maxima in the attribute are aligned with the diffraction apexes, or basically the boulder locations. To find the boulders interactively, we need to lower the threshold, highlighting the amplitude anomalies in the attribute. We need to find the suitable value of the threshold, which highlights most of the boulders and leaves a minimum amount of false positives. Um, Still, we can have some false positives in our solution because we can remove them at a later step. Once we are satisfied with the threshold, we can see that, for example, we are highlighting most of the boulders here. We can click this arrow button to go to the next step of the boulder detection. While we move between the steps, the labeling algorithm numbers all the boulders and measures their sizes. After this, we can hover over any of the boulders and we get its properties, its coordinates and sizes. On the second step, we can set specific bounds for the boulder sizes to remove false positives in this filtering section. For example, here we can remove all the boulders which include only one data sample. This filter specifies the range for the number of cells in the boulder between 2 and 60, and I will be turning this on and off, and you can see how the smaller boulders are disappearing, and they will not be exported into the final table. And the module also allows you to edit the boulders manually. There's an eraser tool which allows you to remove some of the boulders, like this one, for example, and there is this plus tool which allows you to add some of the boulders manually. Like, for example, we can place a boulder here and we can set its size manually, and this new boulder will be exported to the output table together with all the other ones. And finally, when we're satisfied with our editing, we can just export the boulders into a text file. Here I open the export table in an ASCII editor. The table is the main output of the module. You can see that each line corresponds to a specific boulder and contains its properties like the line number, the CDP number, the coordinates, and the sizes. Thank you for your interest in our boulder detection tool. If you are interested in testing this on your dataset, you can request a free trial of the software on the RadXPro website.